Broadcast is now starting. All attendees are in listen-only mode.
Good morning and good afternoon, everybody. Thank you for taking a minute out of your day to attend the webinar for real-world application of generative design. My name is Chris Wilkes. I'm president of IntrinSim USA. We're going to get started in just a second. We've got a couple more people that are logging in through the webinar. Okay, please allow me to introduce a few people, and if you have questions throughout the process of the webinar, you're welcome to use the chat in the question portion of WebEx, log them into there. We will try to make a point of answering those that are topical during the presentation. Otherwise, we'll answer some of them at the end of it. It is my pleasure to present or to introduce our presenters today. First of all, Joe Walsh will be starting off the presentation. Joe's going to give a brief introduction of himself. I've had the opportunity to work with Joe for many years, and he is an expert in the field. I think we're going to enjoy hearing his input. I'll do a brief introduction for IntrinSim and Altair. And then Evan Brennan, who is an Altair applications engineer, will be demonstrating Inspire, and Sean Kroger, who's the U.S. technical director for Altair, will be showing Inspire Print 3D. Again, if you have questions, please feel free to go to the webinar panel, and we try to answer them during the Q&A portion. Okay. With that, I believe, Joe, you have the initial presentation prepared on screen. Please let me hand over control to you.
Thank you very much, Chris. So to introduce myself, I'm Joe Walsh. I'm the CEO of IntrinSim and also the CEO of the Assess Initiative. I've been involved in the CAD/CAM CA industry for about 40 years. And IntrinSim works very closely with software vendors to connect worldwide technology and business. And the Assess Initiative works to foster and enable the simulation revolution for broader use of and benefit of simulation. So what we're going to talk about today is why is 2020 the right time for generative design, and we're going to introduce the concept that we refer to at IntrinSim as a vision for generative design. I'm not going to talk about any particular product capabilities. I think Chris and the team from Altair are going to cover that. What I'm going to talk about are concepts and justifications, reasons, potentials, benefits of generative design in general for anybody who's looking to leverage the capability. So first, we're going to start off with what is generative design. And the Assess Initiative actually worked with several software vendors to come up with a common definition of generative design so that we can get out of everyone having a different definition. And that definition says generative design is the use of algorithmic methods to generate feasible designs or outcomes from a set of performance objectives, performance constraints, and design space for specified use cases. The Assess Initiative goes on and actually describes that those objectives and constraints can include things from multiple areas, including performance, weight, mass, manufacturing, usability, aesthetics, ergonomics, and costs. I think ergonomics and aesthetics are a challenge yet to figure out how to quantify, but we see the whole aspect of generative design growing over time. So what's really important about the definition is generative design is not a particular algorithm or an optimization technology, but instead may leverage one or more optimization technologies and algorithms along with artificial intelligence to create or drive viable designs for outcomes for a specific design scenario. So what we're really going back to as a definition is the ability to algorithmically create designs given a set of criteria and a design scenario. What this introduces is the possibility of a paradigm shift. This means that designs are generated by algorithms, so it enables exploration of a broader range of concepts that an individual would never be able to have time to pursue. It enables generation of effective designs for different or multiple manufacturing processes. So it's actually possible to look at choosing the manufacturing process as part of the generative design design space. It also enables significantly increased design innovation and performance-driven design very early in the design process, which dramatically reduces the design analysis cycles. This enables exploration of a broader range of concepts with dramatically different designs than we've worked with in the past, no longer minor tweaks of what was there before. And so it also enables generation of effective designs for different, well, the same slide. So these things will reduce time, reduce cost, reduce weight, increase quality, and improve innovation, and therefore, by doing those things, improve competitiveness. So the Assess Initiative, and with working in collaboration with IntrinSim, have actually come up with a set of key capabilities that are necessary for software for general applicability. These include, and we're going to go through these in detail, so I won't cover these, but there's 11 capability areas. We've also come up with the concept of a capabilities assessment model, and we've also indicated that if you're going to enable a paradigm shift, you have to actually consider organization and cultural changes. Due to time constraints, I'm not going to discuss the organizational and cultural changes. That would be a webinar in and of itself and then some. But let's acknowledge that they're there because some of the roles, if you implement generative design in a significant way, the roles of who's doing simulation and who's using it at what time will be changing. So it needs to be taken into consideration. Who runs the generative design, for instance? So let's look through the different key capability areas that the software solutions need to be able to provide and that you need to consider as requirements and what level of requirements your application needs. So the first item is handling all appropriate objectives and constraints. Basically, the designer or design engineer who's doing conceptual design today is accounting for a variety of objectives and constraints without explicitly defining them to any software. To be able to replace that effort with generative design, we have to be able to handle the same range of constraints and objectives that the current designs are working under. For that to work for a paradigm shift in the industry, that means that it has to cover a broad range of these. To work for any particular application, it only has to cover those that are related to that application. But different constraint combinations and objective combinations will actually generate different designs. The other issue that we have to deal with is that of handling multiple operational or load conditions. Very rarely do we define anything that is a single load case. So the generative design needs to intelligently work with multiple load conditions. It needs to be smarter than just adding in the material that any load case wanted, because that would be suboptimal. It has to actually intelligently manage the results so that it accounts for the multiple load cases. We also have to handle all of the necessary physics to define the particular problem. To be broadly deployable, it needs to cover a very broad range of physics. When looking at generative design for your application, you need to understand which physics are necessary and make sure that the ones that you need are actually covered by the generative design solution you're looking at. Because similar to, if you cannot cover load cases or physics, then the designs that you're generating are at best ideas to use to base things off of, and they're not directly usable as a design unless it covers the full range of what your scenario requires. The other key item is to enable a paradigm shift is it has to handle multiple manufacturing processes. There's a big, everyone's enamored with additive manufacturing, and that opens up tremendous capabilities and options and innovation, but a significant amount of manufacturing today is still done with subtractive processes. So we're really looking for things where the person running the generative design can choose which manufacturing processes are of interest and can actually compare different designs from different manufacturing processes. That would be the objective, to determine, is there really a benefit for switching from a subtractive process to an additive, or is it actually still cheaper to make this with additive manufacturing? And that brings up the other objective, which is we need to actually handle, to be really truly effective and enable a paradigm shift, cost has to be accounted for in some manner. Because the actual number of parts that you're making influences the cost, and we really aren't interested in generating beautiful, very complicated designs that we can't build because they're too expensive. So the ability to account for cost as a filter is a really important requirement to enable significant use of generative design, because that way you can compare the effectiveness of the actual manufacturing cost as part of the process. We're also looking at handling generative design in an assembly or system context. What this comes down to is actually working at a component level and making sure that the load, you have the appropriate loads on the component that are generated from the system. Causes a limitation that we require a level of expertise to make sure that the loads have been transferred correctly. So you really want to be able to load at a assembly level and have the assembly work the loads down to the component that you're working on. You also may want to work on doing a generative design of multiple components at once, because the load distribution will be a function of the stiffness or conductivity or whatever the appropriate transport mechanism is for the physics that you're looking at. So it's very important to be able to enable generative design at the assembly context so that you can load at the assembly level where it's more clearly understood what the input loadings are, and so you could actually do generative design on multiple components in the assembly. The trick hidden there is that I don't describe in detail here is, to do this well, you have to actually account for the connections and the load transfers between every component. And I believe that the Altair guys have some excellent tools to do that. The other key thing, if we're going to enable a paradigm shift with generative design, is the software needs to enable informed, comprehensive, and efficient exploration of the viable design alternatives. So you should be able to look at a much wider range of design options than a human designer should be able to do, and you should have efficient and effective tools to explore all of the viable design options with either single or multiple design objectives, so that you can actually explore and look at trade-offs from different constraints and different objectives. So we need to provide design explorations that's broader and more comprehensive than it's possible to do without generative design. The idea is to explore a broader space more efficiently. And that brings up the next key requirement and capability, is efficient selection. It doesn't do us any good to generate hundreds or thousands of possible design options from generative design. We need to find a way to work that down to a meaningful set, even though we may have described the problem such that there really are hundreds and thousands of viable designs. We need to include things like artificial intelligence or other approaches and filters so we can get down to a reasonable set of designs for the user to consider. Moving to thousands of designs does not save time, that just moves the effort to a different type of activity. So therefore there needs to be the ability to either control the number of designs created or bring them down to the meaningful design so that quicker decisions can be made. And one of the key things is we expect that generative design is going to be used in the early stages, the concept design stages or early stages of design, to be really effective. In order to do that, further validation, further detailed design, further analysis is still required. So therefore, there needs to be an efficient and effective transformation to detailed design and analysis. The ultimate goal is that transition is fully automated so that not only the geometry comes along, but all of the loads, boundary conditions, the entire design scenario that was used for the generative design maps to the later stage validation and is capable for analysis at a standard finite element software solution. So the idea is to enable that full transition, and the ultimate goal is for that transition to be completely and fully automated. The other thing that's key and important is if we're going to move this earlier in the design process, then the use of generative design means the target user is not the simulation expert, but the engineers and designers responsible for early design concepts and for maturation of the design. So therefore, it has to be well integrated into the designer's workflow or enable a workflow that's suitable for them so that these users actually have access to the software and are knowledgeable how to use it and can leverage the data as an integral part of their design process. Excuse me. It also needs to be broadly accessible. So that it needs to be made broadly accessible for all of those who might be involved in the paradigm shift. So that means flexible licensing, that means easy access, easy setup. So it needs to be available for a wide range of people. So that covers very quickly, probably a little quicker than I intended at first, but very quickly it covers what are the key capability areas that are required to enable a paradigm shift. So that in that process, IntrinSim and Assess Initiative have also turned around. Once the capability areas have been developed, we actually developed a capability assessment model. There is no generative design provider who meets the desired state of capabilities across the full range of the required capabilities for all potential applications. Either they do everything that's required for a set of applications, or they do much of the things, or they do it at a reasonable level, a functional level, but they don't maybe capture everything. And I'm not going to go into details as to where Altair fits in this. They're going to talk to you about their software. What we are saying instead is there is no solution that says, here's generative design that works across all of the capabilities at a perfect, comprehensive level for all of the potential applications. So that's why we developed a capability assessment models so that we can determine where capabilities are and where requirements are. So many applications can be addressed today by the current workflows that are available. And you'll see great examples of that today. So this capability design assessment model enables the assessment of the suitability based on detailed criteria for each capability area. So there's a simple example of handling multiple load conditions with different assessment levels of limited, basic, functional, advanced, and comprehensive, and detailed criteria. And there's another example on the right showing just the limited and basic capabilities required, the criteria required to achieve those for handling all appropriate objectives and conditions. Once the capability model has been created and once it's been assessed, that can be used to determine requirements for a particular design scenario. So if you're interested in using generative design for a particular design scenario, you can look through all of the key capability areas, checking the physics capabilities, checking the multiple load conditions, how does it match against all these criteria, and then you can do the same assessment or have it done for you that indicates how does a particular workflow handle that, and then it's possible for a particular application as shown on the right, looking at two applications, it's possible for all 11 of these areas to determine the suitability index, and you end up with 3 states. One, it's clearly suitable for your application, the generative design workflow, because the mean and the minimum are acceptable. The next state is it's possibly suitable and needs investigation, which would be application 1 here, suitability. The mean suitability index is greater than 1, but there are some that are not suitable and you need to investigate, are they going to give you a problem? And then there's the third classification, which is clearly not suitable, which basically says the mean and the minimum are, the mean is less than the desired 1.0 suitability index. So the suitability index really is determined for each capability criteria by dividing the capability rating by the requirement rating. So it's really a quite straightforward sort of process. So that the capability assessment model actually includes for the criteria a way of quantifying everything into explicit numbers so that very quickly can be used to determine whether or not Altair's solution, for instance, is suitable for an application 1, but maybe not suitable for application 2 because you want to use a manufacturing process that's currently not supported by the constraints. And so that those are the sort of things that you can consider with the capability assessment model. So why is 2020 the right time? Going back, so now that we've gone through the vision. So the vision of generative design is that the paradigm shift is possible. But to enable that paradigm shift, we're going to need to have the ability to assess, we need to have the ability to assess the key capabilities in these 11 key areas. So why is 2020 the right time? One, when it is suitable, generative design can enable a paradigm shift with major benefits. And 2, there is a capability assessment model that is available to determine suitability. So it's no longer a question. You can actually do some assessment ahead of time and then verify that with actually testing the software. And again, so when it does work and it is suitable, it will dramatically reduce time, cost, weight, quality, innovation, and it will improve quality, improve innovation, and improve competitiveness. So the business advantages are there to take the time and effort. The question is when it is suitable, and that's why a lot of effort was put in by IntrinSim and Assess to develop the suitability index in the capability assessment model. Thank you. There's my contact information, and there's further information where you can get a document on a vision for generative design, with much more detail. And there's also a white paper from the Assess Initiative on understanding a generative design enabled design process paradigm shift. That closes my presentation.
Thank you, Joe. Appreciate the presentation. And again, Joe will be sticking around for Q&A part in just a little bit. So I'm going to go into a little bit of information about Altair and NGINSoft, and then my part is only going to be, for those of you on the phone, about 5 minutes, just so we can have plenty of time to get a demonstration of the actual software. So NGINSoft is a authorized reseller of Altair products. We are a reseller in the United States, but the company is a global company. And the US offices are based here in Dallas, but we have offices throughout Europe. The customers that NGINSoft typically works with are many of the company names that you will recognize throughout the world, although given the heavy focus in Europe, you'll see many of these are European based, but quite a few of them in the United States. You see a NASA logo on there and some others as well that are headquartered here. And this is because we focus exclusively on simulation, and this is one of the reasons that we have chosen to partner with Altair in the United States. We do an extensive amount of consulting work. We have over 200 engineers and have completed over 4,000 projects over the 30 years that we've been in business. So there are not many areas of simulation that we are not familiar with. We do quite a bit with FEA, CFD, crash analysis, and of course, one of the leading areas that we're focused on is generative design and the 3D printing. We are, as I mentioned earlier, a software partner of Altair, but we have customers in over 1,500 locations. What that allows us to do is when we come and talk to one of our customers about a particular topic, in this case about generative design, we're able to bring with us, with our engineers, expertise from where we have done work with other customers, what's worked, what hasn't. So if we're going to be talking with you about the Altair products for generative design and topology optimization, we could easily reference the aerospace company in Colorado that we just helped with recently, whose name I don't have permission to use, or we can reference the Department of Energy customer with Altair that we have recently done business with, or oil and gas. So it allows us to bring expertise with Altair products to specific use cases at our customer sites. Our skills are in a wide range of areas. We do quite a bit with the fluid dynamics, with, as I mentioned earlier, FEA and multi-body and high-performance computing. Okay, so about Altair in the simulation-driven design for the topic of this webinar. I think Joe did a pretty good job of explaining what topology optimization is, but essentially, from my perspective, it's a series of mathematical rules, right? So it's an understanding of what is the mathematical rule that applies to the effect that's governing the shape of the particular object, and that can be something that is intuitive, and it might be something that is completely different. So when we look at the Altair Inspire, so you think about this, the topology optimization is really about creating designs that meet the specific performance criteria. So before we would do a design, and then we would go test that design to see if it would meet a whatever the criteria is, and we relied very heavily on the best estimate of an experienced engineer. Now, of course, the experience of an engineer is still highly valuable, but what topology optimization allows you to do is to treat the performance criteria as the primary objective and then create the shape accordingly, keeping in mind the certain constraints that you may have. Okay. Now, if you trace that back, some of you on the phone have been an engineer since the 80s and the 90s, right? And so, you did a lot with the 2D and the 3D. And of course, you were basically starting with some type of a design, and it was generally iterative from whatever your company was manufacturing. You're going to do the next version of it, and I might make a very slight change to a particular device, but I have to keep in mind my historical manufacturing methods and how I could alter that particular shape and still not impact the overall effectiveness of it. As we got more into 3D CAD in the 2000s and 2010, we could do a lot more with the post-processing for simulation, but now we're getting into simulation-driven design. And Altair is at the leading edge of simulation-driven design. And what that means is that we are able to lead with simulation, because if you change in your thought process, and I don't really care about what a product necessarily look like unless I'm in the marketing department. What I care about is what is the functional characteristics of that product. How do I make sure that it performs the way that it should? That means I'm going to lead with simulation and then create products that meet that requirement. So Altair has been enabling simulation-driven design as a company because they are heavily focused on the manufacturability. I know several of you that I've spoken to on the phone in just preparation for this call, talking about manufacturability means that we're going to design something that we can actually manufacture, be that a 3D print manufacturer, be it any of the other manufacturing techniques. Okay. Altair's leadership in the market is not just based on generative design, but also on the other product set and understanding where they're able to apply that technology. And so you've got some videos on the right going and showing that, okay, here's my generative design, but I'm going to take into account manufacturing methods in addition to the additive manufacturing. But this is just one part of an overall suite of products where Altair is leading with simulation. And so we're going to allow for the other engineers on the phone to do a better job of doing a demonstration, and particularly of the generative design products. But you have to keep in mind that these are part of an overall family. And that overall family, because of the licensing structure of Altair, you can have access to these other tools. And for some of these people on the phone, this may be a bit unique, so I'll just go into it briefly. But if you take a look at the interface with the Inspire line, you're able to access all of the different products here because the licensing model that they use is one that's based on a unit-based license. So it's access to the suite. You think of ability to like a lot of software companies, you would just go buy one particular piece of software and you might use it for a couple of days this month and then next quarter use it for a couple of days. Think about this more in terms of you're going to get access to the suite of products and be able to have access to all of the different tools when you need them. And that's the advantage of the Altair system. I've got several people from Altair on the phone that are going to do the demonstration, so they might yell at me for this one, but think about it instead of buying Microsoft Excel and Microsoft Word separately, you bought the Office suite and you're using Word or Excel when you need to, right? And so I like to use that analogy here. Altair at the Inspire is providing a unit-based licensing that gets access to the suite, but is priced for value, okay? And I believe that is my last slide. So with that, I am going to turn the presentation over and you guys are going to see some more details on the products in particular. Evan?
Yep, I'm ready. You want to give me? Beautiful. Can everybody see my Inspire window here?
Sure can.
Awesome. So thanks, Joe and Chris, for the introduction. I'll just jump right into the software and sort of some of the product points and walk through an optimization setup. I'm going to talk about the optimization criteria and different sort of ways that we can control the shape of that optimization before we even run the analysis. And then we'll look at those results and talk about some post-processing. And then I'll hand it off to Sean to do the actual 3D print simulation. So this is the interface for Inspire. This is our generative design tool, topology optimization tool. Can do anything from your basic finite element analysis to a full-blown assembly optimization. So I'll go ahead and just open up a basic parasolid file, just some sort of dumb geometry, and then we'll walk through how to set this up for an optimization. You'll see here I've got a small assembly of 8 to 10 parts, something that might be a motion mechanism or something I could just simulate as a static analysis. So for the sake of this simulation, we'll just set it up as a static analysis. And we'll want to change this shape, this piece here highlighted in yellow. This is going to be the shape that we're going to use the generative design or the topology optimization to change the shape. So up at the top here, you'll see the structure of all of the Inspire tools, whether it's this one or any of the manufacturing tools. Has this ribbon structure where I can click through different sort of workflows that are already built in for me. So we'll start here with the geometry ribbon, and we'll start doing some simplification on this geometry to build it up for optimization. We want to give the solver an ample amount of package space, what we call design space, and Inspire to design. So I'm going to go ahead and use this simplify tool, and I'm going to fill in some of these holes and pockets that were cut out in this geometry. I'll actually go ahead and isolate this part. So I'm just looking at the one that I want to simplify. And then I'm going to click holes, and it's going to automatically search for holes in this geometry that I can fill in. Inspire is really built around being intuitive and useful for designers and people that are familiar with CAD products, but maybe not as familiar with analysis tools. So you see here all the things that are highlighted in red, it'll fill in for me if I accept them. But it missed a couple of these little pockets in the middle for some reason. So I can go ahead and just double click and grab some of those faces and fill them in on their own. I just add all the little fillets in as well. Make sure we get everything that we want to fill in and nothing that we don't. So it's really quick and intuitive just to click through and kind of pick up the faces you want to remove. And then obviously these ones I want to keep for these where these bushings are. I'll just do a control select to get rid of those. So all the faces in red will get removed when I click remove all and filled in automatically. Now I've got a much bigger package space, a really free design space for the optimization solver to work with. I can do the same thing with all the fillets and rounds in the model just to give square edges for a little extra space. Again, that's 2 clicks and it'll automatically remove all of the fillets. And then I could enter into a push and pull mode and maybe pull some of these faces out, to give myself a little bit more geometry to work with as well while we're doing the optimization. So really quickly, that's the geometry tab in the workflow and some of the tools that we use pretty commonly to clean up geometry and prepare it for optimization. All I have to do is set this design space, set this geometry as a design space, and it'll show up in this maroon purple color, and that's just telling the solver that that's the part I'm going to optimize when I click run. That's the geometry I want you to change. So moving on, we'll actually set this up and set up the boundary conditions and the loads and constraints. So in the structures ribbon, everything is, again, working from left to right. So the workflow is really easy to follow and built in for you. And you'll see a lot of these tools highlight yellow in different areas as I hover over them. And that's so that we don't have to click through a bunch of menus to get to a specific tool we want. We just have to know exactly where to click. So really one click to apply a different boundary condition doesn't require me to click through a bunch of different menu files. So I'll go ahead and click the joints icon here because I have some joints that I want to add into this simulation. You'll see, again, it's automatically going to suggest some joints for me, and I can click to accept, or I can go back and find them on my own. But what I'll do is just use the ones that it automatically finds, these concentric joints, concentric holes here in the middle, and automatically click to add a free pin. And I can do the same thing with this other hole. There's another free pin. I can change that condition as I see fit. I can also find my own if it doesn't find a feature that I want to use. I can click this single hole down here at the bottom and add a grounded pin. Grounded pin will just act as a fixed point that will allow rotation, whereas these free pins are allowed to translate and rotate. I've got some boundary conditions set up. I'll go ahead and use this loads tool to apply some of my other boundary conditions that aren't joints. So I can click the apply a support icon and apply a support to any face, edge, or point on the model. And I'll just click this face here in this other joint so that we have a fully constrained model now. Now this is locked in rotation and translation, and then the other joints are allowed to rotate with the grounded pin being grounded. Now we're ready to add some loads to actually drive the stress in the model that will drive the optimization shape. So I'll click the forces icon, which again is a part of this 4-part loads icon. I can click any face, point, or edge to add a force to, and you'll see the face that force is applied to highlighted in red. And these little micro dialogues pop up a lot in Inspire to really help you along the workflow as well. So I can quickly align these with the X, Y, or Z axis, or I could even use a movable triad to rotate in a certain direction that I want. And I can really quickly type in any unit system into here, and it'll convert to pounds. If I'm not working in pounds, or I know my measurement in a different unit, I can just convert it right there. We can quickly apply loads and torques and pressures and things like that to any face, edge, or point along the model. Now I'm all set up with a fully constrained and a loaded model. And there's tons of different capability within this Inspire tool for how to load and constrain your model. So it's not just limited to these basic constraints that we just added. But for the sake of time, these are the easiest to show off, and I think the most intuitive. One of the most important things about Inspire and its workflow for design for manufacturing is this shape controls button. So I can quickly add these shape controls to this design space. What this is going to do is actually tell the solver how I want this shape to look at the end of the run. So these are symmetry planes, for example, and I could say turn off these two because I know I want this part to be symmetric about this plane. And that'll drive the solver to make this part symmetric about that plane. Or I can use these manufacturing shape controls, to say I know how I'm going to manufacture this part, so I want you to optimize it with that in mind. And the one we'll show off here is this overhang constraint. An overhang constraint is going to say I'm going to print this part in a certain direction, and I want you to optimize the overhang angle in that direction. So for example, if I were going to print it here in this orientation, and I know my printer can't handle anything under a 45-degree overhang angle, now the optimization is going to give me a shape that is can be printed with the minimum amount of support structure in this direction. So it'll optimize for print time and support structure volume once you're done with the post cleanup at the end. And we also have these for a split draw or single draw for a casting or molding, or an extrusion as well for a two-dimensional profile. And now we're all set up for an optimization, and we can just go over to the tool here and press run. We can set a different objective, we'll set a different volume we want at the end, or we can actually set a stress target as well if we want to do a minimized mass run. So there's tons of different objectives in here, and we could talk about the different types of optimization until we're blue in the face, but for the purposes of today, what we'll run is a maximized stiffness run, which is going to give me the stiffest possible result with only a 20% of the volume remaining of this purple shape. That's the run we'll take a look at in the next model, and then I'll pass it off to Sean. So here's the result of that run we just set up. This is the exact same model, just already ran in the background, and it took, I think, about 15 or 20 minutes to finish. You'll see here we've got, this is what your standard topology optimization design would look like. A little bit rough around the edges, just due to the process of removing elements and element densities. But we've added some features in Inspire to smooth these shapes out so you can export them, and they look a lot cleaner. So you see there, I'm just toggling on the smooth results button. And then one of the really interesting part about Inspire in this post-processing world is this polyNURBS button. So polyNURBS is going to allow us to take, as Joe mentioned, that transition to a detailed design from a result. So I can use the polyNURBS tool and all of the tools that are underneath this taskbar to wrap this geometry in a clean solid. So for example, I can just kind of click between faces and wrap this geometry all around, or I can build it kind of as a piece by piece. I can build on top of a face in a certain direction. And I can also snap and move any point or edge or face in this model and kind of build it like almost a clay model. But in addition to that, we've added in the new versions what we call polyNURBS fit, and that's going to automatically wrap this shape in a polyNURB. And you'll see it follows the underlying geometry, so it's a little bit more broken and less smooth than if you built it on your own. But what you get out of this is a watertight solid that you can take into any other tool, into, it could be a print simulation, or take the Parasolid file right out into a printer or something like that to set it up for your manufacturing simulation. So you've actually got a watertight solid in 2 clicks of your optimization result, and you can do with it what you wish and edit this with our polyNURBS tool as well. That was a quick walkthrough of optimization and post-processing, and I'll pass this result on to Sean for 3D print simulation.
All right, great. Thanks, Evan. Appreciate you going through that. While you're passing that over to Sean, there is a quick question from Corey. Hi, Corey. And that is, what import options do we have?
We can import anything, any normal solid file. Sean will show you here too. Any step file, SolidWorks file. I think the only thing we can't do is SolidWorks current model year. So like a SolidWorks 2020 file is something we can't open.
Okay.
And that gets updated with the new releases. So the next release will support the latest version of SolidWorks. There's usually about a three-month lag in the new releases to when we fully support those.
And an STL.
Yep, absolutely. We can bring in STLs. On top of that, you saw that wrapping capability that Evan showed. You can bring in an STL and auto polyNURB that as well. So it's certainly something that is very beneficial for the additive manufacturing space, and I highly recommend trying it out. That's been updated in the most recent Inspire release. So I'm going to take a second here and show you also the other brand new product called Inspire Print 3D. So picking up where Evan left off, we now want to run that through a build cycle and simulate what the build process looks like, understand what the thermal and residual stresses are, as well as any deformation that is caused from the printing process. So in this example here, you can see we've got that bracket. We can determine, yeah, there's a little displacement at the top. I'm going to show you how to set that up using that same workflow, working our way left to right in the Print 3D tab. So let's start here with just the bracket, and we'll go into the Print 3D tab and just say what part are we printing. Now here I just have one part, but if you have multiple parts that you're trying to nest on a build tray, you can put in as many parts as you'd like. You specify what the material is. We have a few default materials right now for titanium, aluminum, Inconel, and just move to the next step here, which is defining what you're printing this on. So the default printers that we have are EOS's M90 400, the 400 by 4. We've got Renishaw machines in here and SLM machines. If you're using other machines, let us know. We can certainly help you get those set up. But that's all defining, hatch widthing, spacing, the diameter of the laser, recoat time, and so forth. So when you've selected the printer, it knows what the print dimensions are, and it automatically tries to put that part right there on the build tray for you. So we're going to the third step here in the process, which is to orient this part. When we orient a part, this is going to identify where the support materials are going to be and help us identify what's the best way to place this on the build tray to create a design that is using as little support material as possible, as well as understanding what the print time may be. So here you can see I've got this box that pops up here, and I can just save this initial position, and it's going to tell me what the support area is, the volume of that support, and the estimated print time. I could select, say, max build height, and it's going to reorient it, figure out what's the maximum build height, and update that. So you can see the overall support area has decreased, but the volume of the supports has gone up, and the print time as well has increased. Or I can just specify a surface that I want to orient it to. So I could say I'd like that to be the surface, and again, once it comes back with the results, it will identify the undercuts and show me what the support area is, volume, and so forth. And I can click back in any of these to return to that previous orientation. Right, so let's say we want to use this max build height as our default printing method. So I'm going to accept that, and I'll move over to the fourth step here, which is to actually generate the supports. This takes a couple seconds to do, so bear with me, but what it's doing behind the scenes is it's calculating where all those undercuts were, and automatically creates the supports for you, and then you'll be able to modify and adjust those supports as needed. So like I said, it does take a second because it's creating a bunch of geometry in the background here, but it'll allow you to specify the types of supports you want to use, as well as how those supports are connected to the actual part. All right, so here you can see it's come back with the supports, and I can now make modifications to any of these supports. One of the biggest advantages of Inspire Print 3D is that these supports are tied to the underlying geometry. So I could always go back earlier in the process, make modifications to those polynerves designs, and the supports will automatically update based on the changes to the design. So it's a complete workflow, completely connected. Let's say, for example, I want to move this support and make it more of a tree support. I can simply come over and move this. It automatically keeps my build angle. So let's go to the other one over here. And say I want to move that one out as well. And we can maybe turn this into more of a pin support instead of a solid support. And you can see here we specify what type of connection, and that's defining here on the teeth how tight of a connection it has. So if I change that from weak to strong, you can see that that has increased the teeth size, and you can specify the spacing, the sizing, and do this for pretty much any of the supports you want to simulate. So at that point, once you've got your supports defined, you can come in and look through the slices layer by layer. Right. So as I scroll from the bottom to the top, I can look at any of these layers as I'm going through here. And then I can export that as a STL file. In the next release, we do expect to support the CLI format as well as other 3D print formats in the future. Right now, we write out the STL for the part as well as the 3D supports. And then we want to simulate that. So when we simulate this, we're doing a full thermal mechanical simulation. We can do by layer. We know the velocities, the powder thicknesses. You can specify all these printer parameters. It comes up with the default print for you. And then you can either specify whether you want a more accurate simulation. It'll take much longer, have a finer resolution, or a faster simulation. And then just select run. Now this takes about 10 minutes to solve. So let me go to one that I had already finished here. And what you'll see as we're going through this is the first step of the process is the printing. So it goes layer by layer until it gets to the top. And then once we're to the top, now we go into a cooling cycle, right? So it will cool the material off. And then in the last 2 frames, we're going to actually remove the supports. So the supports were removed in that frame. And then in the next 2 frames, it springs back. Right? So in the last frame, we actually see what the spring back is after all the supports have been removed and it's off the build tray. And we can see the amount of deformation and where it's deformed. We can also look at things like plastic strain, von Mises stress. So understanding where the stresses are in this component after printing. We can put on callouts to understand, you know, what the hot spots might look like, where our min and max are, and we can show that min and max while it actually prints. So as it's changing. Look at nodal temperatures. Right, so understand all sorts of information about the print process. And if you have too much deformation, it's very easy to go back and make changes to either the support mechanism, the orientation, or the design itself to get to a good part before you actually put it in your machine. If you simply eliminate making one mistake on a design, you've paid for the software itself. And as Chris pointed out earlier, this product is fully integrated, so you can do the optimization, the structural analysis, the motion, as well as the simulating of the 3D printing. So with that, I'm going to pass it over to Chris to wrap up the session today and take any questions.
Great, thanks, Sean. So we do have a couple more questions that have come in, and please feel free to type the ones for anybody else on the call. One of the questions that came in is, how long does it usually take for people to learn the software and the workflow? Evan, why don't I start with your answer for that, and then Sean.
Yeah, I think we'll probably agree pretty closely is that our trainings for just the structural side can be done in a day. If you want to do it, I'd say to be like fully versed in it, a 2-day training would be plenty to understand the motion simulation and the structural simulation, static simulation. So I'd say a day or 2 for our certification.
Yeah, I would agree with Evan's assessment. 2 days, a day and a half of training and a half day of mentoring is what most customers do to get ramped up on this. As we add more and more capabilities, like this 3D print tool and the motion tool, that can extend out depending on what you're trying to learn.
Okay, thanks for that. Another question that has come in is the 3D print product that Sean, you just showed. I guess somebody's familiar with the solid thinking units. What is the solid thinking unit requirement for that product? How many?
To do the geometry and the setup for the support piece, that only takes 15 units, just like Inspire does.
Right.
To do the actual solving of the 3D print build process, that takes 30 units. So that is 15 for the geometry and 30 for the actual solving.
Excellent, thank you. Okay. And so we don't have any other questions that have come in. I will turn over to Joe for any final thoughts after you've seen the software shown here.
I was very happy to see the assembly handling and the loading in the assembly context. I was also very happy to see the automatic transition for the polynerbs, making it fit within the design context. And the user interface is clearly set up so that it doesn't require an expert analyst. So I'm seeing several of the criteria that I highlighted being ticked. And I think that it's well worth people taking a look at their scenarios they're interested in looking at, and looking at the Altair solution as one of the viable ones, and doing the suitability analysis. And if the suitability analysis looks good, then they move on and do an actual evaluation.
Very good. Well, then I want to tell everybody thank you for attending the webinar. There's also a question on cost and the software and the units, so I will allow your account representative to work with you directly on that. And if there are any further questions, feel free to contact any of us via email on the follow-up, and we'll be glad to provide more information. We can do, in addition to the demonstration that was shown here, which was a slightly abbreviated version for the time length allowed, if you have others in your organization that you think should see the software, let us know and we'll set up a demonstration for you and your company so you can have the broader team watch how the software can be used. With that, Leah, we can close the call, and thank everybody for your time.